This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on Fundamentals of Probability. Now remember, as good financial risk managers, what we're trying to do is identify the risks and quantify the risks and then manage the risks. And so this first chapter called Probabilities sounds an awful lot like something that we should be doing, that we should be considering inside of those three tasks. Remember how we define risk. Risk can be defined as uncertainty, as variabilities in outcomes, and in terms of probabilities. And so that's really what we're trying to do in Book 2. And please note that Book 2 is much more quantitative, thus the name of it, and so we're going to be technical. And although we're going to be using the financial calculator and our regular calculator a good bit, lots of the challenges are going to be taking some mathematical background and applying it into our risk management principles that we talked about back in Book 1. Let's look at the learning objectives of this chapter. Notice that there are lots of action words: describe and distinguish and define, and then there's one or two: calculate. All right, how about mutually exclusive events? There's a good one here about the turning a car right or left, but let me give you a great example that I give in all of my corporate finance lectures. Let's suppose that you are the owner of a golf course and your golf course is brown. You have there's no greenness on your golf course, and it's because for some reason it just doesn't rain on your golf course. So you think, all right, I need a sprinkler system. So you call a plumber and you say to the plumber, come out and tell me what you can do about the golf course. And the plumber comes out and says, oh, I'm going to put pipes here and there and all sorts of stuff. And so you calculate the net present value and it turns out to be positive. But those of you who are homeowners know that if you have a plumber out to your house and the plumber says, I'll charge you $600 to fix this, you're going to call another plumber. You're going to get a second opinion. So you're going to do the same thing with the golf course. So you call another plumber and he or she comes out and they say, oh, we're going to do pipes, we're going to do whatever. So you calculate the net present value and both of the net present values for both plumbers are positive. Do you need both plumbers? And the answer is no. And this is my great description of a mutually exclusive event. When you pick plumber A, you're automatically excluding plumber B. So what do I have in that first bullet point? They're mutually exclusive if the occurrence of A rules out the occurrence of B. And so, of course, when you're driving a car, you can't turn right and left at the same time. All right, so you have randomly, let's just say you don't know where you're going, so you just randomly turn left, randomly turn right. That's been a fun experience with two of my 4 children who are old enough to drive. They have no idea where they're going at any time. All right, the probability of any two mutually exclusive events occurring is just the sum of the probabilities. And so there we have, the A and the union of B is those two probabilities. Now, how about independent events? This is kind of like the opposite, kind of like the reciprocal of mutually exclusive events. This means that you're evaluating one particular event on its own merits, and the decision to invest in one particular project or choose one particular outcome does not influence the accept or reject decision of any other outcome. How about an example with weather and the stock market? So two random variables, right? The day's weather, however you measure it, with temperature. I think we had that up in an earlier slide. And then the returns on the stock market. What do we know about stock market returns? I bet you guys have heard the term a random walk down Wall Street. So stock prices or stock returns, they might follow a random walk, which means that you really have no idea what's going to happen. But let's suppose that we wanted to figure out what the probability that stock prices will fall and that rain will also fall. So here we go. We got to do this. So tomorrow, the first variable is weather, that it's going to rain. The second variable is the stock market, that it's going to fall. So what we're going to do is we're going to take the probability of the raining and the probability of a stock market crash, or maybe not a crash, but just a decline, and we're going to multiply that. Okay, joint probability is the likelihood that it will rain, and at the same time, the markets will be down. This is probably a fun study to do. I'm not sure that in our risk management model that this might have anything to do with anything that we're doing, although there's probably some relationship between, let's take an example of, let's suppose that we have a client who is a farmer and it rains on one day. That's probably not going to be too big of a deal, but suppose it rains for a month. Well, then stock prices of that farming company will probably fall. How about conditional probabilities? This is a probability in which the likelihood of one event occurring has some relationship, either positive or negative, to one or more other events. Like for example, when, how long has it been? 28 years ago when I got married, my wife and I said, you know what, we love each other, we're going to get married, and boy, oh boy, we sure hope that we're going to have children. And then, so we get married and we have children, and then one day, 15 years ago, we had an egg split. So I've got these 14-year-old twins. And so what does this mean? That there's a probability that we were going to have twins based on previous children, based on our jobs and our income levels, or based on the fact that we got married, or based on the fact that we actually even ever met. I'm from one state, my wife is from another state way, way far away. So sooner or later, these events are going to have a relationship to each other. All right, so what does that have to do with economics here? Let's take an example. Let's suppose that we're thinking about the GDP. So remember, GDP measures the size of the economy, right? So what we're hoping to do as an investor is, if the economy rises, if the economy expands, well, then that increases the probability that the stocks that we own will be able to buy low and sell high. So let's suppose we come up with a 40% chance that GDP will rise, which means there's a 60% chance that it'll either stay the same or fall. Event B is that interest rates will rise. Now, if interest rates rise, what that does is it will tend to make our stock investments and our bond investments less valuable. It will tend to, but it depends on a bunch of other stuff. And let's suppose there's a 50% chance that this will occur. So the question then becomes, what is the relationship between gross domestic product and interest rates? Does one cause the other? Is there some correlation between those two? But clearly, as an economist, you would look at the relationship with GDP and interest rates, and you would think there's probably some relationship there. All right, so a conditional probability is going to look at these two events in relationship to each other. So that what we're going to do is ask the question, what is the probability that there will be GDP growth, which, like I said, has a 40% chance, given the 50% chance that interest rates are going to rise? And here's the good formula for computing conditional probability, and it's relatively simple. Let's do an example here. So we have 100 investors. Some of them buy stocks, some of them buy bonds, some of them buy both stocks and bonds, and then some of them buy something else. All right, if an investor is chosen at random who bought the bonds, what is the probability that they also bought the stock? So what you're tempted to say is, 20 out of 100 purchased stocks and bonds. But what we're doing here is that we're going on this conditional probability assumption is that they have already bought the bonds. What is the probability of them buying stocks? And so I have the solution there in the matrix. And so all we're going to do is take the 20%, which was kind of like the temptation answer, what I said earlier, and we're going to divide that by those that bought bonds. So that gets us to 67%. And here's a good summary table of some of these formulas that I've had in the slide deck. It's probably a wise decision for you guys to work through some examples and to try to memorize those. Suppose we have estimated prior probabilities for events that we are concerned about, and then we obtain new information, kind of like my budget committee conversation in which we send out all of these acceptance letters, and then we kind of wait for them, and then they trickle in, and each time they trickle in, we can get information about those students who decide to accept our invitation to join our school. All right, then what happens, we would like to develop a sound method to compute revised or posterior probabilities. So the more we learn about those students who accept our invitation to attend our college, then the more likely that we'll be able to predict that final outcome. And so this is what Bayes' theorem provides for us. It's named after this dude, Thomas Hayes, who lived in the 1740s and 1750s and 1760s. He was actually the son of a minister, and he became a minister as well. He was an English statistician. So what it does, it helps us use a known outcome to predict a sequence of events leading up to the outcome. That's why I said that my budget committee and enrollment conversation is probably not a really good application of Bayes, because we don't really know how many students are going to show up in September. But nevertheless, that process helps us understand. So the terminology is to use this thing like a turnaround probability, and I'll show you what that means here in just a few slides. But what we do is we gain more information as we go through the process. Let's take a look at an example here. Let's suppose that you're fairly clueless about politics, and so you don't know who won the last presidential election, but you know there were two candidates, a Republican and a Democrat. But what you do know is that a tax cut was recently enacted, and you ask yourself, boy, does that sound more like a Republican or does that sound more like a Democrat? And so you have to figure out which one is the president. Is it a Republican or a Democratic president? So you look at some historical data and you figure that the probability of a Republican president completing this tax cut policy is 80%, whereas a Democratic president would only be 20%. So can these probabilities help you determine the probability that the sitting president, given that a tax cut was recently enacted, is a Republican or a Democrat? And then, yeah, Bayes' theorem helps us do this. What do we know? We know the probability of a tax cut given that the president is a Republican or a Democrat. But what we want is the probability that the president is a Republican or a Democrat, given that there has been a tax cut. So we know there has been a tax cut. We don't know which party the president belongs to. How about a financial example here? Let's suppose that you know the probability of a certified hedge fund manager earning an excess return or outperforming the benchmark, assuming it's the market portfolio is X%. You also know that the probability of a non-certified manager earning an excess return is just Y%. All right. Now, if you know that a manager has actually earned an excess return, so you just randomly pick a manager and this manager has generated an excess return, can you figure out that what the probability is that the manager is either certified or non-certified? And the answer is, of course, yes. So what do we have? We have the probability of an excess return given that the manager is either certified or non-certified, right? But what we want is the probability that the manager is certified or not certified, given that what we know, there has been an excess return. Let's take a look at a simple case here. So here's the Bayes formula. On the left-hand side of the equal sign, we have the probability of event A given that event B has occurred. That's called a conditional probability. And that's equal to, on the right side of the equal sign, we're going to take a ratio. The probability of B given A, this is also a conditional probability, but this is taken from the data. We also have in the numerator the initial belief of probability A occurring. We call that a prior probability. and then we have to divide by the probability of event B. And what that does is it forces the probability distribution to sum to 1. All right, let's take a look at this in a little bit more detail. And so note, what do we know about conditional probabilities? The probability of A given B can be defined as the intersection of A and B divided by the probability of A. That's what I have at the top left there. And then the opposite of that is the conditional probability of B, given that A has occurred. And so notice that in the numerator there on the right-hand side up at the top there, I have the intersection of B and A divided by the probability of A. Now, of course, what we know, this intersection A and B and A, they both mean the same thing, right? Think of, those sets that you have when you're in the 5th grade or whatever. And so intuitively, A and B and A are identical. All right, so I can put that equal sign there, and then I can do some substituting, and I can do just some cross multiplying, and I can deduce that. Notice I have those arrows there pointing up there, and so that's just showing you where to cross multiply. And so we can get that formula there, and then we can divide both sides by B, and that gives us our Bayes theorem. So what I have in the blue box there is the same thing that I have in the blue box there. Now this is the simplest case, and so let's take a look at it at an example here. You guys know I like to give sports analogies and sports examples, and given the fact that I still have not started my tax return in the however many days it is before April 15th. Let's suppose it's April 15th. You file your tax return at 8 o'clock, and you're rewarding yourself by going out to play golf. And so you look outside and you see a cloudy sky. You want to play golf today, but you know that April is a rainy month wherever you live. And so let's just suppose that it on average, it rains every other day in April. Now you know that 60% of cloudy days will end up being rainy days. And you also know that 45% of all April mornings are cloudy. All right, so here's our question. What is the probability it will rain during your round of golf, given that today, April 15th, it's a cloudy day? All right, so what do? We start with the probability that it's going to rain given clouds. So what do we know? What do we know here? That it's April 15th, right? April has 30 days, so if it rains every other day, so I guess I'm just assuming they're 50%. So we're going to multiply that 50% by the 60% chance that cloudy days will end up being rainy days, and then we're going to divide by the 45% because all April mornings are cloudy. I'm sorry, 45% of all April mornings are cloudy. And so that gives us a probability that it's going to rain during our round of golf today on April 15th of 67%. And see how this Bayes theorem adds to our understanding, because just a simple application of some simple statistics would be that April is a rainy month, it rains every other day, so you would think that we have a 50% chance of being rained on today, right? That's just a simple deduction. However, we have some more information. We have the information about cloudy days and the relationship between clouds and rain. So we use all that stuff to refine our estimate of the probability of rain from just a simple, naive 50% all the way up to 67%. Now, this can be applied over different sets of probabilities. So there's the general Bayes theorem, the general case in which we can do this for I equals 1 and 2 and 3 and 4 and all the way out to n. Now let's make sure we understand the difference between these prior and posterior probabilities. So the prior probability is the probability of an event before new data is collected. Like let's go back to my sons losing their phone. The probability of them losing their phone is 100%, but the probability of them losing their phone on any given day is clearly not 100% because they haven't lost it 100% of the time. The probability of them losing their phone today depends on how many hours they play Fortnite, how much homework do they have, are they going to basketball practice, etc., etc. All right, so notice what I have there in that first bullet point. It's the best rational assessment of the probability of an outcome based on existing knowledge. But then a posterior probability is the revised or updated probability taking into consideration new information. So if my boys if they playing Fortnite and they have basketball and they have homework, who knows what's going to happen to that phone? All right, so we start with the prior probabilities, then we gain the new information, then we apply the Bayes formula like we did in the golfing example, and then we can come up with these posterior probabilities. How about going back to our previous examples here? A priori probability would be the probability that the president is elected is Republican, or the probability that he or she is a Democrat. A posterior probability would be the probability of a Republican president, given that there has been a tax cut. Let's go ahead and do some more math here in example 3. All right, let's suppose we have a consulting firm bidding for a consulting contract. So the firm's management feels that it has a 50% chance of landing the project. However, the client to whom the bid was submitted subsequently asked for additional information. All right, so there's that 50% chance, but now the client has asked for more information. Well, clearly, more information about whatever the client wants information, that can help us refine that probability. All right, so from historical data, we know that a client asked for additional information for 70% of successful bids and 40% of unsuccessful bids. So what is the posterior probability that the bid will be successful given a request for additional information? So we can put together a matrix there. So down the left-hand column, we've got the event, successful, which means obtaining the contract, unsuccessful, which would mean a rejection of the contract. And so the probability of an event, 50%, right? We go back here, we have 50% chance of landing the project. And then the probability of additional information is 70 and 40. And so all we need to do is apply those probabilities into the numerator and to the denominator, and that refines us back up to a 63%. Because what do we know back here? Given a request for additional information, and so you're tempted to jump that up to 70% right, but it doesn't quite go there. It goes to 63%. How about another example? Suppose you are an equity analyst and you use historical data to categorize portfolio managers as being either excellent or average. And so you have some rubric where you put them into one of those two categories. All right, now let's add some more information. 20% of fund managers are excellent and 80% are average. So the probability of a manager outperforming the market in any given year is independent of their performance in any other year. And by the way, that's been shown by lots and lots of financial research, is that historical outperformance for mutual fund managers really doesn't actually predict future outperformance. In fact, some studies show just the opposite, that outperforming managers tend to underperform. Maybe that's an application of reversion to the mean. All right, so let's take a look at a new fund manager, which started 3 years ago, and this fund manager outperformed the market all 3 years. So what is the probability that the manager is excellent? All right, so let's put together that table. We've got down the left-hand column, excellent and average, and there's the probabilities, 20 and 80, and then probability of beating the market. And so let's go ahead and just apply those probabilities into the numerator and the denominator. And then remember that when you do this series of steps, we're going to do this over 3 years, so we need to raise it to the third power, and that just goes back to a simple application of like those old time value of money principles when you're compounding, and when you do the same thing with probabilities, you got to multiply those probabilities. So raise those probabilities of beating the market, so 1 and 2 and 3 years, raise it to the third power. So that gets us up to 57%. And I think that takes us through the learning objectives for this chapter. Be sensitive to the learning objective action words or command words, there you have a describe and a compare and an apply. So that probably means that you're going to have to do some computing or some calculation. And by the way, you'll probably have to do some calculations as well if the action word says something like distinguish, maybe even an explain or demonstrate. So you probably should be aware of the math, even though it might not sound like it.